In this unit, we will learn another test to determine whether or not series converge or diverge. This test, or tests actually, are called the comparison tests, and they allow us to compare a series to a series where we know whether or not it converges or diverges. So first, a quick question. So do you think that this series, the sum from n equals 1 to infinity of 1 over 2 to the n plus 1, do you think it should converge or diverge? Like, what's your sort of feeling about it? What does it look a lot like? And what I would say is, if this 1 were not there, then you would have the sum from n equals 1 to infinity of 1 over 2 to the n, which technically is a geometric series with r equal to 1/2. So it feels as if this series probably should converge because it's pretty similar to this geometric series. And that's going to be the basic idea in today's lesson, is that if you look at a series and think it's kind of like something where you know what that something does, and often the something you're going to compare to will either be a geometric series or a p-series. Those are kind of your two go-to comparison things. And the behavior of the series you're given will be similar to the behavior of the series you're comparing to. So the first thing is something called the direct comparison test. So you assume that you have two series, and this test will only work if they have positive terms. If the terms aren't positive, it falls apart. And you assume that the an is less than the bn for all n. Okay, the first thing is that if your sum of bn's converge, then so does your an's. And think why this probably is true. The sum of the bn's is the sum of the terms that are larger. So if the larger converges, so must the smaller. I think that should kind of make sense. If you're adding up things that are bigger and you know that these other things are smaller, well, that's got to converge too. And the second thing says if the smaller one diverges, then so does the larger. So if you add up these numbers and you know that that diverges, well, then adding up even bigger numbers will have to diverge too. So those two ideas should probably make some sense. The whole positive terms thing will come into play when we make this into make the partial sums into increasing sequences. Okay, so let's start by defining some partial sums. So we're going to let S sub n equal the nth partial sum of the A sub n's. So sum from I equals 1 to n of ai. Let Tn be the sum from I equals 1 to n of the bi. And we're going to let T equal the sum from n equals 1 to infinity of bn. And we'll let S equal the sum from n equals 1 to infinity of an. We're just going to need to give these partial sums names, and we have to give them different names because we have two different series that we're summing. Okay, so first thing to notice is that since both series have positive terms, the Sn and Tn are increasing sequences. Increases instead of increasing. Increasing. Okay, so first let's prove the first one. Let's assume that the sum of the bn's, let's assume that thing converges. And then we know that the partial sums Tn approach some value t. And since An is less than or equal to Bn, we know that Sn is less than or equal to Tn. So since Sn's a sum of all the An's up to a point and Tn's a sum of all the Bn's up to a point. And then it's also true that Sn is less than or equal to T. And T is the thing that Tn is converging to. And once again, that means that Sn is an increasing and bounded sequence. So thus the sequence of partial sums Sn is increasing and bounded, and therefore convergent. And this means that the sum of An converges. Okay, so we have shown the first case that if the larger sum converges, so does the smaller sum. Okay, next let's assume that An diverges. So suppose the sum An diverges. Then we know that the partial sums Sn are going to go to infinity. But we also know that Ai is less than or equal to Bi for any I. And so thus your nth partial sum of Sn is less than or equal to Tn. And if Sn goes to infinity, then Tn has to go to infinity as well. And therefore the sum of Bn's diverges. So to apply this test, you have to establish that you have a series that is less than a known convergent series if you're trying to prove convergence, or greater than a known diverging series if you're trying to prove divergence. So here, this is a lot like 1 over 2 to the n, which is a geometric series. We're going to try to prove convergence. So first start by noticing that 5 plus 2 to the n, that's bigger than 2 to the n. And if I reciprocate both sides, you have that 1 over 5 plus 2 to the n is less than 1 over 2 to the n. And also these things are all positive, so bigger than 0. Now give me a short explanation as the sum from n equals 1 to infinity of 1 over 2 to the n converges. Tell me you know why it converges. It's a geometric series with r equal to 1/2. The sum from n equals 1 to infinity of 1 over 5 plus 2 to the n converges by, tell me the test you used, direct comparison. This next series looks a lot like 1 over n. And so to prove this diverges, we have to prove that 1 over n is smaller than 1 over n minus 2. If the smaller diverges, so does the larger. So you start by noticing that n minus 2 is less than n. And then 1 over n minus 2 is greater than 1 over n. And as the sum from n equals 3 to infinity of 1 over n diverges, you can tell me that that's the harmonic series, or you can say it's a p-series with p equal to 1. The sum from n equals 3 to infinity 1 over n minus 2 will also diverges. All right, why can't direct comparison be used to test the following series for convergence or divergence? We try to apply the same method. We say, okay, well, 2 plus root n, that's bigger than root n. And so therefore, 1 over 2 plus root n is less than 1 over root n. Okay, so this is the one that you know diverges, but this one is smaller than it. The problem here is that your inequality goes the wrong way. You know that if the smaller diverges, so does the larger, but if the larger, put this in words, if the larger diverges, you can make no conclusions about the smaller one. And a similar thing here, we try to establish an inequality. 2 to the n minus 1 is smaller than 2 to the n. 1 over 2 to the n minus 1 is bigger than 1 over 2 to the n. So we know the smaller series will converge, but the larger, decay. We think it probably should converge, but the question is how would you do that? How would you show that? And when you run into an issue where the inequality is pointing the wrong direction, we're going to use a different but related test called the limit comparison test. So here's what that limit comparison test says. It says, suppose that you have two series, once again with positive terms. If you limit the ratio of those terms, and the limit goes to some value c, where c is a finite positive number, then either both series converge or both diverge. So this will allow you to compare series even if you cannot use direct comparison. So let's actually establish why this is true, because it's not terribly difficult. So we start by letting lowercase m and uppercase m be positive numbers, such that that c value we find is in between them. Little m is less than c, which is less than big M. And we know that because an over bn approaches this c value as n gets large, for a large n, there is a value of capital N such that eventually that ratio, that an over bn, is in between our little m and our big M, as long as the n is bigger than or equal to that capital N. So if you go far enough out, far enough away, eventually the an over bn is sandwiched in between these two things. Multiplying both sides by bn, we have m times little bn is less than an, which is less than m times little bn. Okay, so here's what we know. If the sum of bn converges, so does the sum of the number m times bn. Multiplying by a constant won't affect convergence. And then the sum of an will converge by direct comparison. So we've shown that an and bn do the same thing. If bn converges, so does an. If the sum bn diverges, so does the sum of little m times bn. And since an is greater than little m times bn, then the sum of an's also diverges. So this establishes that this is okay. This tells us that if you take a ratio of the terms of one series with another series, and that gives you a finite number, both series will do the same thing. Okay, let's apply that to a particular example. So if you're going to use this particular test, you need to tell me what an and bn are. So let's let an be the terms of your series. And let's let bn be the terms of a series you know something about, 1 over 3 to the n. Then find the limit as n goes to infinity of an over bn. I'm going to write this down the long way once and then skip this step. 1 over 3 to the n minus 1 over 1 over 3 to the n. Notice that that denominator is going to reciprocate. That will happen every single time. So we have the limit as n goes to infinity, 1 over 3 to the n minus 1 times 3 to the n over 1, which simplifies a little bit more to the limit as n goes to infinity, 3 to the n over 3 to the n minus 1. And you could either L'Hopital rule this, or you could divide the numerator and denominator by 3 to the n. Either way works. You get the limit as n goes to infinity of 1 over 1 minus 1 over 3 to the n, which is 1. Okay, now as your sum from n equals 1 to infinity of 1 over 3 to the n converges, make sure you tell me why. Say it's geometric with r equal 1/3. The sum from n equals 1 to infinity 1 over 3 to the n minus 1 also converges. All right, with the previous one, it was kind of obvious what to compare to. So here, we'll let the an's be the terms of in our series, so 2n squared minus 5 over 4n to the 5th plus n squared. To figure out what to compare it to, I'm just going to look at the biggest powers in numerator and denominator. N squared over n to the 5th would reduce to 1 over n cubed. And the series with the terms defined by that bn will be a p-series that converges because the p is equal to 3. So let's find the limit as n goes to infinity of an over bn. This will need to be a finite number, and once we know it's a finite number, we know that the series will do the same thing. It'll be times n cubed over 1. So distributing that n cubed, we'll have 2n to the 5th minus 5n cubed over 4n to the 5th plus n squared. You've done enough of these limits to know that since the degree of the numerator and denominator are equal, this limit will be 2/4 or 1/2, and that certainly is bigger than 0. And so thus, as the sum from n equals 1 to infinity of 1 over n cubed converges, tell me you know why. It's a p-series with p equal to 3. The sum from n equal to 1 to infinity of all that craziness also converges. And we probably should say by the limit comparison test. Because now we have quite a few tests where we have some names. All right, this series, so 1 plus sine n over 10 to the n. This will actually be direct comparison. So the first thing to observe about sine is that -1 is less than or equal to sine of n, which is less than or equal to 1. So sine n is in between -1 and 1. So then 1 plus sine of n is less than or equal to 2, bigger than or equal to 0. And so 0 is less than or equal to 1 plus sine of n over 10 to the n, which is less than or equal to 2 over 10 to the n. And as the sum from n equals 1 to infinity, 2 over 10 to the n is a convergent geometric series, r equal to 1/10. This series also converges by direct comparison. I think here establishing an inequality probably would be pretty tricky. So let's try the limit comparison test. We'll let the ANs be 5 plus 2n over 1 plus n squared squared. I think it'd be best to expand that out. So think about that as 5 plus 2n over n to the 4th plus 2n squared plus 1. And let's define our bn's. The highest power in the numerator is 1. Denominator is n to the 4th. Let's compare to 1 over n cubed. So that tells us we're probably going to have convergence. So then the limit as n goes to infinity of an over bn, 5 plus 2n over n to the 4th plus 2n squared plus 1 multiplied by n cubed over 1. So 5n cubed plus 2n to the 4th over n to the 4th plus 2n squared plus 1. That limit will equal 2, which is certainly bigger than 0. And as the sum from n equals 1 to infinity of 1 over n cubed converges, it's a p-series with p equal to 3. The sum from n equals 1 to infinity of 5 plus 2n over 1 plus n squared squared also converges by the limit comparison test. Whew, this one. Okay, so I think it would be completely futile to try to establish any kind of direct comparison with this one. So limit comparison is your only option. So we'll let the ANs be the terms in your sequence. Okay, now when we consider the highest powers, the highest degree in the numerator is that n squared, and the denominator is the n to the 6th. But that n to the 6th is rooted, which makes it n to the 3rd. So you really have something that's about n squared over about n to the 3rd. So you're going to let your bn, in this case, actually be 1 over n. So this series, if you can prove that this limit is some finite number, this series will diverge. So find the limit as n goes to infinity of an over bn. Okay, distribute that n in the numerator. Okay, so you should have the limit as n goes to infinity of n plus n squared plus 2n cubed over the square root of 1 plus n squared plus n to the 6th. So now I'm going to multiply the numerator and denominator both by 1 over n cubed. In the numerator, that's not terribly difficult to see what happens. You should be able to do that. Got the limit as n goes to infinity 1 over n squared plus 1 over n plus 2. Now let's think about what happens with square roots. If you have, say, square root of, we'll say, 9 times 2, when that 9 comes out, it gets rooted. So if I wanted to put it back in, I would have to square it. So when this 1 over n cubed goes back inside of that root sign, it gets squared, and it becomes 1 over n to the 6th. And then distributing that 1 over n to the 6th through, we get 1 over n squared plus 1 over n plus 2 all over square root 1 over n to the 6th plus 1 over n to the 4th plus 1. And now you can see the 1 over n squared, 1 over n, 1 over n to the 6th, and 1 over n to the 4th, those all go to 0. So this limit goes to 2. And so both series will do the same thing. So as the sum from n equals 1 to infinity of 1 over n diverges, either tell me it's harmonic or say it's a p series with p equal to 1. Let's just summarize that the given series also diverges. All right, back in the vein of estimation, so let's use the first 10 terms to approximate the sum of this series, and then let's estimate the error. So S10 will be equal to 1 over 1 plus 1 cubed plus 1 over 1 plus 2 cubed, etc., up to 1 over 1 plus 10 cubed. That's about equal to 0.682. Okay, so what we know here is that 1 over 1 plus n cubed is less than 1 over n cubed. So we know this series will converge by direct comparison. Okay, and we know that the remainder for this series, if we add those up, will be less than adding up those things. So we can estimate the error for this sum, and then the error for the sum we're looking at will be less than that. And we estimate this using the integral remainder. Okay, so let's call the remainder of this thing T10. That's less than or equal to the integral from 10 to infinity 1 over x cubed, excusez-moi, dx, which equals the limit as sum b goes to infinity, integral from 10 to b, x to the negative 3 dx, or the limit as b goes to infinity, negative 1/2 x to the negative 2, evaluated from 10 to b. So that will equal the limit as b goes to infinity, negative 1 over 2b squared plus 1 over 2 times 10 squared. So that's 1 over 200. And so since we know we have this inequality going on, the remainder for our series R10 will be less than or equal to 1 over 200. So making that bound depended upon us being able to do some kind of direct comparison thing. But the point is you can use direct comparison and then integral tests to also estimate how much you are off by.